In this lecture sequence, we'll look at fossil fuels in more detail in terms of how they form and how they're used. We'll examine the origin of different types of fossil fuels and their formation processes. Then we'll look at some of the methods and practices for exploring for fossil fuel deposits and their extraction. And then finally, we'll look at some of the estimates of how much oil or natural gas is available and the reserves in the context of its use and origin. So to begin with, a couple of major terms when we talk about fossil fuels. First off, what's a fossil? Take a moment and write down a definition as you understand it. Okay? Something of a textbook definition, which varies but is generally referred to as the remains or trace of something that was once living in the past, and generally we're talking about things that were living in the geologic time, or generally tens or hundreds of thousands to millions or hundreds of millions of years ago. The organisms involved may be plants, animals, or other microscopic organisms. And what's key to understand is that these fossils were preserved, or the evidence of their once living was preserved in what are considered fossiliferous rocks. And these may or in formations or in sedimentary layers. And fossiliferous simply means that it's fossil containing. Fuel, on the other hand, you should write down a definition for. Okay? That's as a general term, not specifically referring to fossil fuels, but fuels in general are any material that can undergo some sort of a chemical reaction or a combustion reaction to release the stored potential energy within the material. In the general sense, we're referring to both carbon-based compounds and also nuclear materials, but that's only under the general use of the term, not specifically with fossils or fossil materials. There are many different types of fossil fuels, but the five of the major ones, and the first three of which we'll consider in more detail, are coal, oil, natural gas. Two that may become more important in the future are what are called tar sands and oil shale. And coal, I think you may have a general picture in your mind of as being a rock, consolidated rock, black in substance or black in appearance, and it can be burned in a combustion reaction to release heat. Oil is a liquid state of matter, and it comes in different grades or characters. Very heavy crude oil, medium weight crude oil, or what's referred to as light and also sweet crude oil in terms of its chemical properties and physical characteristics. Gases, natural gases comprised of different types of molecules, can be propane, methane, or benzene molecules in a gas dispersed form. Tar sands are, as the name implies, sandy granular material with heavy, thick oily material in the intergranular spaces. And then oil shale is a form of rock, shale, which is a consolidated rock, that has oil embedded in the matrix or the pore space between the grains of the rock itself. So there are a variety of different types, and there are different properties, and gives rise to different uses and different consequences, depending on the type of material it is. There's a general sequence of fossil fuel formation that's true of all the types, and it begins with the input of light energy from the sun being passed through space to the earth, and plants absorb that light energy and convert it to chemical stored energy through the process of photosynthesis. That can be in terrestrial plants or in marine single-cell or simple-celled plankton or other microscopic organisms. Plants mainly, although animals certainly do this as well, they will eventually die running through their life cycle. They then undergo a variety of decomposition processes and form organic matter, which is undifferentiated, kind of complex chemical suite of molecules that over time will accumulate in thin or thick layers. Further chemical reactions consume the oxygen, and physical transport processes remove the oxygen from the area of these layers, and they become anoxic, or lacking oxygen. Once those layers are deposited, then there is a process of burial, and that's derived from sediment, either from a terrestrial case or an oceanic case. Mineral soils or mineral sand, silt, clay type particles and rock fragments bury the organic layers, and eventually those layers undergo increasing pressure and temperature. And so you need high levels of pressure and temperature, but not necessarily too high, because if the temperature, for example, becomes too great, it can actually cook the organic matter beyond what would form the fossil fuels we're familiar with and concerned with here. Once that burial occurs and the temperature and pressure create the right conditions, there's a suite of chemical reactions referred to as diagenesis that transform those organic layers into the fossil fuels we see. And again, an example of a fossil here, coal material with embedded plant traces shown on the bottom. And then the sequence up on top is the general formation process for coal, where back in geologic time, we'll talk about this shortly, about 300 million years ago or so, large forests and organic swampy materials died and accumulated. Subsequent erosion of the landscape surrounded the area buried that and then started to compress and heat up that material. And then the chemical reactions formed precursors to the fossil fuels that we're interested in, say, of coal, and eventually the hard coals form at the final stage and are left in a resistant or persistent state that survive to the modern time that we mine for and excavate and extract for coal use. So again, there is a difference if you consider marine conditions, the ocean, well over 70% of the Earth's surface, and terrestrial conditions. And the fossil fuels are characteristics of the two major types. In marine environments, you'll find oil and natural gas forming, and the plant-like organisms that are the major source of organic matter are the phytoplankton. These are the microscopic, very small organisms, green plants, that transfer light energy coming in over the surface of the ocean into their plant tissues or microscopic tissues, and then eventually that breaks down as they die and then sinks to the bottom of the ocean and collects up in large layers. And historically, back in time, there were conditions where, with the right temperature and light conditions, there was high degrees of productivity producing these. The upper picture here shows a zone of phytoplankton imaged from a NASA satellite sensor that was able to pick up the chlorophyll in the plants. It shows that these blooms can be rather extensive and rather concentrated depending on currents and energy conditions and nutrients available. In terrestrial environments, you have a different form, and primarily it's coal is formed under terrestrial source conditions. And it's macroscopic, large vegetation associated with swamps and forests that occurred. And historically, hundreds of millions of years ago, the continents were in different position, and many of the large continental masses were in a more equatorial zone, and with large amounts of incoming solar radiation, higher temperatures, abundant moisture, there were massive and ancient forests and swamps that ended up creating much larger concentrations of organic matter that led to the coal formation than we might see forming today with the different distribution and orientation of the continents. Coal formation as a process, again, dates back to over 300 million years ago And it's a period, the Carboniferous period, where there was that really abundant forest system, and the swamps associated with that were very, very, very productive in terms of plant material. And when that plant material again dies and decomposes, it leads to a very anoxic or reduced condition where you have swamp gases and methane gases, and characteristic rotten egg odors are indicative of that. The material that was deposited can ended up in the modern era as being near the surface with subsequent burial and then erosion, wearing down surfaces in mountains and keeping it at or near the surface. And at the current time, mining at depth for underground mining can extend to almost 1,000 feet below ground surface for profitable coal seams. And again, the general process summarized here as in the earlier one is that there was the original organic plant era, the deposition of dead plant material in the organic area was buried by what's referred to as dirt, but as sediment, and eventually the burial results in the environment in which the coal can form. Oil and natural gas formation, however, again, is under a marine environment, and it's different from coal in a very fundamental way, is that as the liquid petroleum or gas materials, they are able to move and migrate within the subsurface through cracks and voids and fissures, but they're also, as liquids and gases, more susceptible to degradation, breakdown, and chemical destruction, decomposition, even once formed. And so the amount of oil formed has been recycled several times through natural geologic processes in the subsurface. It's estimated that about 60% of the oil we currently have identified through reserves and suspected resources are fairly recent and date back only 66 million years before present. And that if we went back 100 million years ago, we'd probably find roughly the same amount. So there is something in the way of a recycling process that goes on and replenishes current rates, although the formation literally takes tens of millions of years. And as you might guess, knowing that even though these form under marine conditions, there are several continental areas where oil and natural gas is found, and their formation had to occur when those areas were formerly under oceans or shallow seas. That's the case of the Saudi Arabian Peninsula, which is where most of the world's current oil reserves are located, were in the geologic past when that oil was formed, were underwater. Again, diagrammatically, is that all ocean life, and dominantly the phytoplankton, not so much the animals shown here, were, as they died, created a rain of organic material that built up on the layers, and eventually those organic layers were covered by subsea or underwater sediment deposition, and they were buried and eventually were cooked into the oil and natural gas deposits. And then they may have been, through changes in the Earth's surface and plate tectonic movement, there may have been actually transfer from ocean conditions to continental conditions, and there may be thick layers, hundreds or thousands of feet of sand, silt, rock, and other materials on top of the oil and gas deposits. But these are what are drilled through to extract for current production. Oil and natural gas are the deposits we find for commercial exploitation are referred to as reservoirs, and the reservoir formation process is rather distinctive as well. As we noted, both as liquids and gaseous materials, oil and natural gas can migrate and will migrate due to density and buoyancy upward through rocks or pores and voids in the rocks, and travel up to the layers until they reach some sort of an impervious upper layer, or what's called a cap rock. And this traps the oil and natural gas and allows for the formation of larger collections or deposits of these fossil fuels to accumulate. Again, from the textbook, this diagram here shows the curved nature, this anticlinal formation that gives rise to an underground structural feature to where the upward moving gas, which is the lightest typically, and then the underlying oil will migrate and then trap. And there may also be, and typically is water, groundwater, associated with the lowermost area. The reservoir rock in this situation is those rock layers in which the oil and natural gas are formed. Above that is some form of cap rock, and that's what is impervious enough to allow for persistent accumulation of the oil and natural gas until such time as drilling may occur to move into it. So you can imagine, and this from the surface with no evidence of where the materials are, you may drill dry wells to great depths, not even see the oil or natural gas until you're able to identify where the anticline or other structural feature that might have caused the material to accumulate and persist. Tar sands, again, as the name implies, you can visualize sand, and this, though, rather than just pure sand material that you might find on beaches, is a combination of sand, finer grained materials called clay, water, and bitumen, which is a precursor to oil and coal, and it's an organic petroleum deposit. Its characteristics are very heavy, black, viscous, very thick, almost sticky oil, and hence the name tar, and it holds together fairly well. And if you can imagine, trying to get the oil away from those individual grains of sand out of a lot of different small pores is very difficult. It's too thick to pump. The fine grained material around it is not rigid like the rock materials with the fractures that contain the oil and reservoir formations for oil and natural gas. Thus, you can't pump it, so instead it requires some form of mining and then an extraction process to occur once the material has been brought to surface. And this can cause widespread destruction of land surfaces and ecosystems, much as surface coal mining, which we'll talk about shortly. However, the process of extracting that oil is very expensive and complex, much more expensive than you would find from extraction of conventional oil and natural gas. Thus, tar sands are viewed as a source of oil and other petroleum reserves only at such times that the price of oil and the availability of other supplies is so limited that the cost will pay for the expenses of extraction and production. Likewise, oil shale has similar issues, and it's a sedimentary rock that is, again, it has a rock-like character similar to coal, but it has significant amounts and overriding amounts of silt and clay, fine-grained particles, but embedded within the matrix is enough kerogen, which is another oil precursor liquid, that the material is fairly significant. The amount of fossil fuel within the rock is fairly significant compared to standard shale rock. Again, these bituminous materials are in the solid phase. They can't be pumped. They can't be readily taken out of the ground using conventional drilling and extraction methods like you would for oil. The reason is that they form at subcritical temperatures and pressures that would contribute to, or needed to, create actual oil formations and deposits. Likewise, similar to tar sands, they must be mined, and the oil has to be extracted by heating the rock to fairly high temperatures. So if you can imagine, if you're trying to extract a fossil fuel, but you have to spend energy, a considerable amount of energy, combusting some sort of fossil fuel to heat the rock material to extract the oil, you can see that this is a very inefficient way to obtain oil from this oil shale. And likewise, it also has very significant potential environmental hazards because the extraction process and the waste produced are very toxic. Some review questions. Which fossil fuels tend to form under terrestrial conditions? and which ones form under marine environments. You should be able to summarize and describe the process of fossil fuel formation. And then finally, what is a caprock, and perhaps know what its significance is with regard to fossil fuel. This completes our first section of Lecture 7. You should read the relevant sections in the chapter and move on to the second part. In the second part of the lecture, we'll look at some of the processes and techniques for exploration for oil, natural gas, and other fossil fuels, and also for the extraction of those materials from their geologic environments. We'll review some of the exploration methods, including drilling and pumping, and specific mining, both subsurface and surface, and we'll look briefly at transportation and processing. The exploration methods started out very simply. The earliest oil deposits to be used were seeps, where oil surfaced naturally to the ground surface through upward migration. However, once oil's different uses were observed and understood, and the demand for oil grew, then it became apparent the need to find more active forms of exploration to find oil underground. Early efforts were areas where, say, oil was observed at the surface, and from early understandings of the geologic environments involved, to drill wells, and with the tall structure, be able to add pipe drilling deeper and deeper into the ground. More modern systems involve offshore drilling. As time went on and there was discovery that significant oil deposits were under the ocean, and typically the continental shelf areas, structures and technology and drilling techniques and new drilling platforms were developed to allow the same sort of exploration and drilling into under ocean environments. These are forms of active exploration where, based on some sort of geologic inference or mapping, the idea that there may be oil leads to drilling as a way to actively determine if the oil or natural gas is present and how much is there. Drilling is also useful for drilling for coal deposits to determine their depth by drilling a hole in the ground and taking a core out to determine the nature and type and extent of coal deposits. Another area of techniques for determining the presence of hydrocarbons and the underlying geologic structures are geophysical surveys. Seismic surveys, there's an example of it which in your book, in a supplemental section, where some sort of a shot is fired or an explosion is set off, and that sets off sound waves that travel through the subsurface, reflecting or refracting off of the different formations and coming back to various sensors. And the travel time in these of the sound wave from the source to various geophones allows for an estimation of the thickness and extent and depth of various types of strata. And then from there may be other geologic information and or exploratory drilling to determine whether or not any of those perform caprocks that can trap oil or natural gas. So there's a whole host of different exploration methods and techniques for determining where and how much oil or natural gas might be, or coal might be present. Once the initial drilling is done, and again, it may go from a preliminary exploratory drilling with very small rig that can drill relatively shallow depths to larger drill rigs that can go hundreds or thousands of feet deep. Then, once a well has been determined to be able to produce oil, the standard oil derricks with the pumps moving or something you'll see fairly typically, especially in various areas of California, can go on. And if an oil field is particularly productive, and historically there have been cases where there have been numerous wells drilled and pumps installed in very close proximity to one another. If you can, try to guess which major city in California this historic photo is taken from around 1930. This is what is today an urban area of Los Angeles. The LA basin and surrounding basins had significant oil and natural gas there originally, and there's some ground sinking or subsidence that occurred as significant quantities of oils were pumped out. However, the overall basin deposits were relatively limited and exhausted, and as the fields ended, the derricks and pumps were removed, except for a few areas today that still provide some extraction, and they've been replaced obviously with the urban centers we're more familiar with today. Pumping and recovery of oil is not as straightforward as you might think. Recall that the oil is found in cracks and fractures and openings in rocks, and as such it's very poorly connected and sometimes difficult to get the oil out. Typical pumping and what's called primary recovery can access up to about 15% of the original oil in the reservoir rock formation, leaving us the larger majority of the oil still underground and not accessible. Secondary recovery may inject water to try and force oil up to into a position or into fractures and voids to where it can be extracted. And so water flooding and water injection can incorporate enough fluid to increase the output by up to another 20% of oil. But again, this still leaves the majority, or about 2/3 of the oil, potentially in place. Most modern systems now will extend to what's called enhanced recovery, and this incorporates steam or something else, some other air fluid, but typically steam is the most common one, to reduce the viscosity of the oil and enable it to flow more readily and to enhance its extraction. And also there's some slight pressurizing of the fluids that may cause them to migrate to the pumping area as well. So the overall recovery process is not as efficient as you might think because of the difficulty of getting all the oil, or as much oil as possible, out of the myriad voids, fractures, cracks, and other openings in the rock formation in the reservoir. Turning now to underground coal mining, the history of coal mining is particularly striking if you look at some of the historical photos. Cases where small seams, not much thicker than the width of shoulders, where miners would actually crawl underground and pick, break up, and hand move rock or fragments of the coal back out to openings and back to surface eventually. I've seen openings in small family-run coal mining operations that were not much taller than this. This is one of the reasons that teenagers and even children were involved in being able to fit into some of these areas to access seams of coal that were too small for adult males to move around in very easily. Larger openings and more involved tunneling operations involve shoring and other forms of safety. Gradually, rail cars would move the material back to common shafts and out to elevators to bring them up. These techniques persist today. This is from this decade in China, where underground operations and coal mining still involve human effort and hard physical effort to do this. It's a very dirty, dangerous, and unhealthy environment. Black lung and other respiratory diseases are common, where the dust coming off of the coal has within it very toxic chemicals, and actually within the hydrocarbon dust even small traces of radionuclides. So lung cancer and other forms of respiratory disease are fairly common with long-term coal mining professions. More modern and more mechanized forms of operations are room and pillar, forms of long wall mining. There's an example here where you'll find whole areas of large openings where machinery can run on rails and scoop and extract much larger quantities than individual miners can, or even groups of miners can. And the pillars are left to support the overlying rock, so the whole system in the above ground surface doesn't collapse or sink catastrophically, but then as much extraction occurs between the pillars as possible. These are passed out to a conveyor belt, sent to some sort of another train of ore cars, and eventually elevators to bring it back up to the surface. This is a much more involved and commercial and high-tech level of mining, which has replaced some human operator, but there's still quite a bit of quite a bit of individual miner activity involved in many of these activities. Surface mining for coal is visibly fairly striking. One of the more common types is what's called strip mining. And this is done typically in areas with relatively flat terrain, but can include areas with low rolling topography. And what happens is, as the name implies, the ground is stripped away in layers to remove overburden or overlying rock to expose the coal seams in progressive fashions working backward. And again, this is probably more typical when the uppermost coal seams are very close to the surface, and subsequent layers are still within relatively close proximity. And you'll find strip mining throughout much of the United States, but in many areas of the Midwest, and more commonly in western deposits is where you'll see this somewhat more commonly than the subsurface mining. Another form of mining, what's called mountaintop removal, occurs in areas that have fairly steep slopes and valleys, and these are areas typically in the eastern United States where whole hilltops are taken out, much as a strip mine, but also removed. The process of removal is to take the material out to expose the coal seams. And this is predominantly in the eastern United States, and probably within the eastern United States, the Appalachian region, through Kentucky and states to the West Virginia and states to the north and south is where much of this activity is going on. The strip mines themselves use drag lines, or what are large shovels that remove the overburden layers, and these have to be huge in order to move landscape scale quantities of rock. The seams that they expose and can access then can be from mere inches up to over hundreds of feet. And again, the surface disturbances left behind, I think you can see in this picture, for a given coal seam can be rather substantial. As the coal is mined out, what's left behind is completely disturbed, low nutrient or no nutrient rock fragments and unconsolidated sediments. Mountaintop removal, as a process, removes the overburden or the rock layers above the coal seams, but it deposits the waste rock and soil materials into the adjoining valleys. So it's a valley fill situation, where each layer that's taken off above the coal seam has to come somewhere. And the simplest, most cost-effective way to remove the top is simply just to push it into the valley below. They have a effect, though, on the valleys where eventually will fill in, the material will erode, it can fill in streams, cause stream channels to migrate and move, flooding out mining communities in the valley bottoms. There's a lot of waste material. The waste rock can be very toxic in terms of having certain mineral deposits that, once exposed to the air, lead to acid mine drainage and other forms of chemical degradation of water quality. It's a very complex area, and what's left behind is very infertile, essentially bare rock ground, and the valley fill is filled with mining spoil. So the whole area, over twice the original mining area, has had a degradation of its soils. It's virtually impossible or not cost effective, according to the mining companies, to maintain the topsoil. You can't, or they won't, stockpile it to put it back out onto this area. And whatever minimal plant growth to meet reclamation demands is minimal and very relatively short-lived. And so rather than having a productive forest, the original valley, mountain and valley province, you'll have a relatively flattened, almost plateau-like area with poor grasses and non-native species. That's what's left behind. So mountaintop removal remains a fairly controversial practice in the mining regions of Appalachia. This concludes our second portion of the lecture. We'll move on now to the third portion. In this third and final part of this lecture, we'll look at some of the resources and reserves as far as their outlook for availability and development in the future. We'll revisit the notion of resources and their contrast with the reserves in terms of how much of a given fossil fuel we have available. We'll look at specific reserves for oil, natural gas, and coal. So to begin, recall the chart we showed earlier where resources, and whether it be oil, natural gas, or coal, starts out being a fairly uncertain and something that's estimated or inferred or interpreted from some sort of geologic evidence or understanding of, say, a particular geologic formation as containing coal or oil deposits. With time, as further understanding and exploration and such may incorporate it, there you may discover that these are probable resources and are maybe in an early stage of being considered reserves. And so as the initial guessed resource becomes more certain, then it transfers from the category of a resource into the area of a reserve. Another thing that's important to understand is that resources may not, and oftentimes aren't, cost-effective or profitable, especially if you have to go in and drill several wells or many wells at hundreds of thousands to millions of dollars per well to try and search for and identify the extent of an oil field or a reservoir. So as the resource becomes a reserve, meaning becomes better known through characterization, mapping, and additional exploration, then the cost effectiveness and the ability to determine whether or not these are profitable quantities of fossil fuels available, then they come fully into this reserve and proven reserve category, where you'll have sustained profits and maximum profits, and you're very confident that when you go to drill or to tunnel or extract the material or remove a great deal of earth materials, that you'll end up with the optimum quantity of the particular fossil fuel you're looking at. So again, when we talk about resources, fossil fuel resources, we're talking about the most general sense of the fossil fuel material. And when we talk about reserves, that's how much we can really more or less count on, or at least count on with a high degree of reliability. For crude oil, our reserves are shown on this table, and the plot demonstrates that there can be additions to oil reserves or reductions in oil reserves based on the production and removal during the year or new discoveries. What you'll notice here is that in around the early 1970s, there was a major discovery and an estimation of significant oil identified in Prudhoe Bay on the north slope of Alaska. New oil added in given years are shown here in individuals. So there have been very few deposits or discoveries that have matched that find on the north slope. And that the total amount of or the total reserves then are the sum or combination of additions minus domestic production in a given year. So our reserves in domestic oil are relatively limited for the U.S. Recall also that we talked in an introductory way about some predictions for fossil fuel, in this case particularly oil production, based on the work by M. King Hubbard with the U.S. Geological Survey in the 1950s and early 1960s. Coming out of the oil industry and the U.S. Geological Survey, Hubbard did some of the really outstanding work looking at existing data and understandings and mappings of reserves and known, or at least resources of a certain degree of confidence, and past production rates and consumptions to estimate how fast and how long we could produce oil in the United States and in the world. And he predicted that there would be a peak of production and then gradual declines over time, and came up with estimates of the timing of those peaks both for U.S. production and for world production. For the U.S. production, he estimated it would occur during the 1970s, and in fact that proved to be very true. The domestic production has declined progressively since the peak in around 1977. Global productions were also estimated by Hubbard, and he determined or predicted that the world oil production would peak during this decade, between 2000 and 2010. Now, subsequent to that work, probably 40 years ago or more, there have been new discoveries, improved data analysis, and what we find is that and also better information about consumption and economic forces that affect production rates, and that's caused this estimated peak to be extended out in time or pushed out later into this century. However, what you'll find is that most estimates occur, or at least predict, that the peak of world oil production will occur sometime between 2020 and 2047. Although some observers and industry analysts and critics of the industry believe that, after looking at the data, that we may have already peaked in oil production. So there still is a certain degree of debate over when peak oil is here, but there seems to be a general consensus that world peak oil production is due to occur sometime the first half of this century. So this is production now. And in that includes offshore oil, and that's controversial as well because it's a more difficult resource to explore and to estimate and then to quantify and to determine reserves. The technologies involved for exploration production are very expensive and much more involved and prone to storms, rising sea levels, a great deal of, and just a harsh environment. In a saltwater, corrosive environment is very difficult to keep machinery, equipment, piping, and so on running. And there's all manner of different exploratory rigs that are some that are locked to or embedded or attached to the ocean floor. Various towers and derricks that attach up to the surface, and the various other platforms that allow these materials to drilling to occur through drill stems. And then, of course, there's the requisite piping to transport any discovered oil back to land sources and for storage and refining. One of the big concerns, of course, over offshore oil is the fact that, remember, this is on the continental shelf. This is in relatively shallow water, not in the deep ocean. We don't have the technology at the current time, or at least it's not economic, to consider drilling or trying to extract oil in deep water. Although there are some early efforts and some exploratory efforts to examine develop the technologies needed for that. But at the current time, we're talking about offshore but nearshore sources, and there's significant potential for pollution of coastal systems and general background oil pollution of the oceans, because these are, again, as any mechanical process or industrial process with humans at work, there is the prospect for errors, accidents, equipment failures, and so on. And there have been some rather catastrophic leaks and spills that have polluted the oceans and the coastal zones, which we'll talk about in the next lecture. So from a production point of view, we've considered it. Now what's happening on the demand or consumption side? If you look at this plot, you'll see that the lower graph is pretty much these are the industrialized nations that, for the most part, probably better than 80 or 90%. Although after 1975, world consumption has increased at a greater rate due to increasing demand from countries such as China and India that have undergone rapid industrial growth. But the overall trend for the world production is steadily increasing demand. So if demand is increasing, as peak oil is approached and ultimately reached, there's going to come a conflict or a problem meeting this demand by just increasing production and expanding new fields to produce oil. So again, we have two different views of this. We'll look at it in a moment here. And it's important to note that over the last decade or two, the United States has attempted to reduce its dependence on Middle Eastern countries by exporting more oil from Western Hemisphere countries. And we'll look at the sources of that later on. However, the actual oil supply physically may trade hands and change hands, and the supply system is so closely linked and the global markets are so closely interrelated that whether the oil physically comes from Iran or Iraq or from Mexico or Venezuela, the price of oil and the competition for oil increasingly, which is driving prices up and reducing supplies more rapidly, really doesn't matter where the oil comes from. However, it's very likely, given the sources of the oil and the reserves, the fact that the Middle East still has, together with Saudi Arabia, approximately 65% of the known oil reserves, and that the other sources of Latin America, Africa, these other small non-Middle Eastern sources simply will not be able to meet demand for a very long period of time. And so ultimately, even though we are importing more non-Middle Eastern oil at the present time, we will ultimately have to return to greater dependence on Middle Eastern oil once these Western Hemisphere and other sources begin to decline much more rapidly. And the use of oil, again, as we've said previously, the United States is the dominant user, along with Western Europe, Japan, and Russia. Note that China is increasing, and also India, which doesn't even show up on this chart, but is lumped in with the 38%. Both India and China have the potential to rapidly overtake the United States as the major oil consumers. And this in turn is going to drive and motivate exploration and attempts to optimize and increase production as long as possible. The outlook for fossil fuels in general is very, very, very grim for domestic sources. We're going to have increasing dependence on imports, both in oil and natural gas. And it's been noted repeatedly that we do have a rather large, and probably the largest, supply of coal in the world as far as domestic supplies go. Although there are significant issues of using coal, which we'll talk about in the next lecture. Table 7.1 shows this, that based on United States reserves and production rates, we have a very limited lifespan for all fossil fuels except for coal. The supplies and the deposits are so extensive that it's estimated that in their current use and projected growth in current use, they could provide their needs for over 250 years. Other natural gas and oil in particular are very small and will not supply our needs pretty much past the end of the coming decade. The outlook for natural gas resources is similar in terms of to those of the prospects for oil, and the distribution is not surprisingly similar to oil, because recall that the reservoir formations that you find oftentimes are capturing both oil and natural gas at the same time. because the formation process of the two fossil fuels through diagenesis occurs roughly in parallel fashion. Not completely, but there's a very close correlation oftentimes between oil reservoirs and natural gas deposits in the same or nearby rock layers. The largest reserves, not surprisingly, for natural gas are in the Middle East, except for Russia. Russia has an unusually large supply of that, because of its location, its latitude. The materials that give rise to natural gas were different there. The problem is that natural gas, as a gas, is much more difficult to transport and distribute, as opposed to moving a liquid. Natural gas is volatile, it's gaseous, it's more explosive, more prone to leaks because it has to be named in pressurized pipelines or transport ships. The world reserves, and oil and natural gas reserves, like you say, you'll find quite a comparable trend in that Saudi Arabia has the largest oil reserves and some of the highest natural gas reserves. Ironically, Russia, which has considerable oil reserves, also has by far the largest natural gas reserves. And this is a source of income as it's been rebuilding since the end of the Soviet regime in the late 1980s. The United States is low on both, and the other countries listed here, likewise, are relatively minor suppliers other than primarily for their local or regional needs. Coal reserves are recoverable reserves. Again, the United States has the largest supplies, and one of the problems, though, of taking advantage of these is that there is a major concern over their probable contribution to greenhouse gas accumulation in the atmosphere and global warming. And likewise, given the presence of sulfur dioxide, nitrogen oxides in the combustion gases that come off of coal combustion, lead to widespread acid rain damage occurring throughout areas downwind of coal-fired power plants. World sources show that the United States and Russia are the two largest owners of domestic coal supplies. China has a very large supply, which is of concern because as they've used a lot of it for rapid industrial growth, it's also, again, a very dirty burning substance and has big implications for greenhouse gas emissions and also for production of local air quality problems. There are four major types of coal: lignite, subbituminous, bituminous, and anthracite. And each has slightly different carbon percentages as part of their differentiation. And accordingly, there's a difference in their energy content, or their ability to stored energy that can be released during the combustion process. And gradually, you'll find that the energy content is correlated with the carbon content. But also in there, like I say, the sulfur content, for the most part, to some degree nitrogen, because these are organic matter compounds. Sulfur, as it's burned, has the ability to come off as sulfur dioxide in the atmosphere that can react with rainfall and other moisture types like water vapor to create acid rain. The distribution of U.S. coal deposits, based on the formation in the distant geologic past, is shown pretty much throughout much of the United States. Rocky Mountain states have large deposits of the subbituminous. Lignite is also dominantly in the west. In the eastern United States, you have the bituminous and also anthracite. Appalachian region is the area here. This is the area that has a lot of the problems with mountaintop removal. The mines in this area tend to be more deep mines than underground mines. And surface mining, again, would be the primary practice. Strip mining would be the practice here in the Midwest, Great Plains, and then the area upper Great Plains, and also in the Intermountain states. However, with these regional regional differences in deposits, each region has its own problems associated with that, and some of these problems pose potential constraints on their ability to produce optimal amounts of coal based on the available resources. In Appalachia, for example, the mountaintop removal is causing significant damage to waterways, flooding, sediment buildup, and degradation of water quality. It's also of concern because it does constitute a loss of productive forest land, which is a much more renewable resource from the standpoint of providing jobs, local employment to economically disadvantaged rural parts of Kentucky, West Virginia, and adjoining states. In the Midwest, any major expansion of strip mining would probably come into direct conflict with the direct loss of very productive agricultural lands, which in the future there will be a tension then between the desire or economic incentive to produce more energy traded off against the ability to produce as much food as possible for a growing world population. And then finally, in the Rocky Mountain states, many of the same problems associated with strip mining are of concern, and there's also conflict that in some of these cases there is competing desire to protect public lands for recreation, endangered species, and other ecosystem values. But also the same concerns over loss of or damage to waterways with erosion and water quality occur as well. This concludes our discussion of fossil fuel formation and the resources themselves. We'll turn now to the next stage, which is the 8th lecture on fossil fuel use practices.